simple example or simple whatever the structure of a deep learning model or neural network. Neural network is called as deep learning. The fancy words, right? Artificial intelligence, data science, data analytics, right? All these are fancy words. I would say data analytics may be a bit uh, like visualization and analyzing data kind of a thing. But there also they use machine learning, deep learning. So they call it as analytics team, and then they start using all data scientists and all. But statistics involved in a project where machine learning, deep learning is involved is called as data science project. Purely AI projects will be very rare. If you have, if you are building a robo with one kind of, hardware, all one kind of unique hardware, then there will be no distributional change in the data we collect. The sensors, the cameras, everything are same. So there will not be much difference in the data distribution. So you can directly start AML project. But in real time, it is not going to happen. Right? So some experiments you will use some devices, other experiments you may use other devices, and you may collect everything and try to use it while building a model. Right? So that way, every project is a data science project. Every AI project is a data science project. These are all terminology. So deep learning we call it as. When there are more than one hidden layer, you call it as a deep neural network. That's where deep learning came in. Okay. Artificial neural network, ANN, means all the neural networks, whether it is deep neural network, shallow neural network, convolutional neural network, recurrent neural network, all neural networks, transformers, everything is artificial neural network. Natural neural network is our brain. Artificial neural network is the one these guys designed. Okay. So deep, that is artificial neural. Deep neural networks, DNN is a neural network that has got more than one hidden layer is called as deep neural network. So you understood, right? Input will go to all the nodes. All the nodes will try to understand pattern. When the weights are different, the pattern recognition is going to be different. To pass it to this node, we need three weights: theta 0, theta 1, theta 2, theta 3. Theta 1 will multiply x1, theta 2 will multiply x2, theta 3 will multiply x3. That's we add these three, that is called a linear combination. And then we substitute that linear combination into a sigmoid function, 1 by 1 plus e power minus, right? When the weights are different, inputs are same, right? But all the four nodes inputs are same. When weights are different, the outcome is going to be different. So initial iteration, it's going to be random. Here all weights random, all weights random, all weights random, all weights random. You get some y cap. There is a y. There will be a cost function which will measure the error. Based on the error, we'll adjust these weights. How will we adjust? In deep learning, in gradient descent, we were doing that, right? So theta is equal to theta minus alpha into derivative of the cost function with respect to theta, right? So here theta, there are many functions in between, right? Derivative with respect to cost function, I am saying. Here we have cost function. After calculating y cap, we have y, we have some cost calculating metric here or the function here. So if you want to adjust this weight, theta 1 is equal to theta 1 minus alpha into derivative of the cost function. When you say cost function, it is a function of all these variables. Okay, this is just an introduction, right? I'll take you through in more in detail how exactly that calculation is happening. Okay, so if you take this theta, you want to adjust now that theta is equal to theta minus alpha into derivative of, again, cost function is a function of all these variables. So definitely we need to use chain rule. So on a logistic regression gradient descent itself, we use a chain rule because only there are two functions in between. But on a neural network, right, we should definitely use chain rule. I'll show in detail. Okay. Before we go there, why deep neural network, right? Why not? I'm saying machine learning is not useful as soon as you get into high dimensional spaces, right? Why not? Okay. Suppose that, where is that? Yeah, suppose that you have to do a decision boundary like this, and you have 10 features in your data set. Okay. If you have to build a logistic regression model, you have maybe 50 features, 50 features, 50 x1, x2, and so on, x50 you have in your data set. Now you want to do a non-linear decision boundary using logistic regression. One logistic regression, no neural network. Only one logistic regression. You wanted to do a non-linear decision boundary. What you should do? You have 50 features in your data set. Okay. You want to do a non-linear decision boundary with logistic regression algorithm. What we should do?
Polynomial.
Yes, sir. Polynomial, right? So you need to apply polynomial transformation to the data. Then you pass it to the logistic regression hypothesis function. What is logistic? Sigmoid function, right? So you have 50 features. You have to do a very complex nonlinear decision boundary. What is the degree of the polynomial? Can you guess? What could be the degree of the polynomial?
Come again, sir.
You have
Maximum number of features.
50 features, input features, and then you wanted to do a very complex non-linear decision boundary, and you said polynomial features is the class you need to apply onto the data, right? With what degree we should be applying that polynomial features? With what degree? Degree 2 is enough, 3 is enough, 4 is enough, 10 is enough.
We need to check the learning curve, right?
Yeah, learning curve, but ultimately, if you have to do a very complex nonlinear decision boundary, the degree is going to be high, right?
Yeah.
Give me one second. So degree of the polynomial is going to be very high. Suppose that I have taken 10 as the degree. I have 50 features and I have taken 10 as the degree. How many features will come in the data set if you apply polynomial features?
There is a formula n into
N plus d factorial by n factorial into d factorial, right? So that is 60 factorial by 50 factorial into 10 factorial. Is that a big number? Is that a big number?
yes,
sir.
obviously.
Right? So you cannot do a very complex non-linear decision boundary with machine learning. That is first problem. Okay. But with AI, right? But with deep learning, you can definitely do a complex non-linear decision boundary with simple neural network. Okay, this example is like that. I have taken data like this. 1 1 y is equal to 1, 1 0 y is equal to 0, 0 1 y is equal to 0, 0 0. So when both are 1 or both are 0, the y value is 1. This is basically XNOR. XNOR gate it is. Okay. Don't be worried about XNOR. Right. This is the data set. We have to build a model that actually predicts. Now when you pass both are 1, it should predict 1. When you pass both are 0, it should predict 1. Otherwise, it should predict 0. That means the decision boundary should be like this. See, 1 1 is this point, 0 0 is this point, 1 0 is this point, 0 1 is this point, right? So these two belongs to one class, these two belong to another class. That means there should be a decision boundary distinguishing these two classes, right? So maybe I did very curvy line, but you can actually take a something like that also, right? Like a pipe also. Okay. So a decision boundary should be like that. Do you agree? Do you agree with this?
Yes.
Right. I'm moving on. So to do this, right, I am going to build a neural network like this. So this is very key, very important. Let me explain this. And then, this is the basis for whole No deep learning. Give me 1 second. So it's a small data set. So I am actually going to do manual assignment of weights. Give me 1 second. So I have to produce a neural network that gives me when I pass 1 1, 1 will be the output. When I pass 0 0, 1 will be the output. Otherwise, it should be 0. So that kind of neural network, that kind of model I should build. Okay, this model will do that. Okay, so let me try to show how it is actually doing. This +1, right? This is called as bias term. Okay, whatever you pass, you may pass 1 1 here, 1 0 here, 0 1 here, or 1 1 here. For all of them, it is going to be 1. This is called as bias term. Okay, this part is called as bias term. I think we know, right? We already know this. So, and for every layer, right? This is the input layer. This is the hidden layer. Right? And this is output layer. Okay, for a hidden layer also you have the bias term. Okay, so bias term is there for to generate the theta 0 thing, right? So now let us look at this particular node. This is a logistic regression node. Suppose that this is a logistic regression. Don't look at ends and knots and all that. Okay, this is just a logistic regression node. This is just a logistic regression node. So on a logistic regression node, these are the 3 weights. Okay, suppose that the neural network already learned weights. Okay, I ran all this data for multiple iterations, and then it actually learned the weights. These are not random weights. These are all learned weights. All complete. The model is working now. Okay, so now if I pass 1 1 into this network, right? What happens here? Can you tell me? Inside this node, what is happening? What is happening there?
1 into minus 20.
1 into
1 into
minus 20
plus
plus
1 into 10
1 into 10 plus
1 into 15.
1 into 15, that 15, right? So minus 20 plus 25, right? That is equal to 1 by 1 plus e power minus 5, right?
Yes.
In logistic regression, I told you that if the linear combination of the inputs is positive, the record belongs to 1, right?
Positive class, yes.
Right? Positive class, right? This, whatever this outcome is going to be e power 5 by 1 plus e power 5. Right? That's going to be greater than or equal to 0.5. So this is 1. Okay. If you pass these values to this node, this is also logistic regression. Okay. So if you pass these values to this node, what happens here? 1 by 1 plus e power minus of plus 20 minus 25 minus 25. Right? Is that correct? Plus 20 1 into minus 20 minus 20. Yes, this is a negative number, right? This is going to be 0. Is this a negative number? Minus 50 plus 20 is going to be minus 50 plus 20 is going to be minus 30. Minus of minus is going to be positive. It's going to be 1 by 1 plus e power 30. Right? Denominator is too high, so it's going to be less than 0.5, not equal to less than 0.5. Right? So it's 0. Now, this is also a logistic regression. Right? 1 by 1 plus e power minus 20 minus half minus 20 plus 0 plus 25. This is again positive number. Is this a positive number? 25 minus 20 is 5, right? So 1 by 1 plus e power minus 5. That is actually greater than or equal to 0.5. So this is 1. See that? I passed 1, 1. I got 1. Okay, if I pass 0, 0, right, I'll get 1. See this, 0, 0. I'll pass 0, 0 now. I'm passing 0, 0 now. Right? If I pass 0, 0, this is minus 20. This is going to be 0. This is going to be 0. Right? So, correct, right? 1 into minus 20 minus 20, 0 into 10, 0, 0 into 15, 0, right? It's going to be plus 20, right? It's going to be less than, right? So it's going to be 0. When I pass the same 0, 0 to this network, right? It's going to be 1 into 20, this is 0, this is 0, right? This is equal to minus 20, right? 1 minus 20, right? Here it is minus 20. That's greater than or equal to 0.5, so it's going to be 1. Right? Now if I take this, right, so 1 by, not this one, I think I should have adjusted this one, minus 20 and greater than, so that's okay. 1 by 1 plus e power minus half minus 20 plus 25 plus 0. So this is again positive, right? 1 by 1 plus e power minus 5, that is greater than or equal to 0.5. So this is 1. So when I pass 0, 0, I am getting 1. When I pass 1, 1, I am getting 1. If I pass 1, 0, I will get 0. Let me pass that also. 1, 0, I am passing. Right? So now let me calculate here. 1 by 1 plus, right? For this network, I am for that node, I am calculating. E power 1 into minus 20, right? Minus half minus 20. 1 into 10, 0. Right? This is equal to 1 by 1 plus e power minus half minus 10 is plus 10. That is equal to less than 0.5. So this is 0. Okay. And for this network, for this node, for this node, 1 by 1 plus e power minus half 20. This node 1 into 20, right? Minus 25 plus 0. This is equal to 1 by 1 plus e power minus of minus 5 is plus 5. That is also less than or equal to 0.5. This is also 0. Now the final output node 1 by 1 plus e power minus of minus 20, right, plus 0 plus 0. This is equal to 1 by 1 plus e power 20. This is less than or equal to 0.5. I got 0. Right? You pass 0, 1, 0, 1, you get 0. This is the simple network which is actually doing, which is actually giving us a very complex decision boundary, right? So if you look at this decision boundary, right, you don't care about how the line was drawn there, but if you look at the outcome, the network is satisfying. If you have to build this kind of a network, this kind of a model using machine learning, it is going to be very difficult. It may make the data set very complex. Okay, did you get the gist of it? How neural network is actually, simple neural network actually creating a complex pattern recognition? Did you get it? Did you get it? Any questions there?
No, sir.
Okay, good. Right now, right? What I'm? Yeah, go ahead.
Sir, this is the hidden layer, right? Not x1 and not x2, and x1 and x2 is the hidden layer, right?
No, this is, I'll talk about that. Don't be worried about it.
I'm talking about just the hidden layer. The first one is input layer, and middle one is hidden layer, and last one is output layer, right, sir?
Yes, and yes.
And yesterday, like Grigor said, like here that input, whatever like y cap is hidden layer, it's a become is a x, right? Coming to the output layer.
I didn't get your question, sir. Could
For
you
example,
తెలుగులో చెప్పండి సార్ పర్వాలేదు నన్ను తెలుగులో
అట్లాగా సార్ ఇది హిడెన్ లేయర్ లో ఉన్న వాల్యూ అన్నది వై క్యాప్ వాల్యూ వస్తుంది సార్. ఈ వై క్యాప్ వాల్యూ నీకు నెక్స్ట్ లేయర్ వెళ్ళినప్పుడు అది ఎక్స్ అవుతుంది కదా సార్.
అవునండి, అదే చేశాను ఇక్కడ నేను. మనం 0.5 తీసుకోలేదని మనం. ఓకే ఓకే, you're asking like why didn't you took the value like that, the actual logistic regressions outcome. This outcome is going to be decimals, right? Why didn't you took it? Even if I take that value also, it will come that way only. For explanation purpose, I have taken the value. But if you calculate those carefully and put them into the logistic regression also, you will get that only. But these weights may change. Okay, for these weights, right, I actually, for understanding purposes, what I did is I took some weights which are actually satisfying this particular condition. Now I am the neural network. I understood the weights. Right? Any model based learning algorithms, ultimate goal is to understand the weights. That's what I'm actually coming to, right? You asked the right question. Right, so any neural network or any algorithm, whether it's a machine learning algorithm or a deep learning algorithm, the main purpose of the algorithm is to understand these weights. If I change this -25 to 20, will the output come the same way? If I change it to +20, will the output come the same way? The model will predict the same, 111 and 001.
May not be, sir.
May not, right? So what is it? The total network is driven by these weights. So the algorithm, the neural network's main goal is to understand these weights. Now I have taken the logistic regressions outcome, prediction as the value 0 or 1 here, right? 0 or 1. But Narayana is asking, why did you took 0 or 1? You should have taken a number between 0 and 1, because logistic regression, this whatever function, right, that will give you a number between 0 and 1. If I took number between 0 and 1, right, these weights will change. I may have to change these weights. I may have to carefully, calculate these values, put them, and then change these weights in such a way that it gives the 111 and 001. For understanding purposes, I did not do that. Got it? For our simplicity.
Sir, I have a different opinion here, sir.
Yeah.
Because, for example, in the hidden layer, whatever those nodes are there, they are also models like, let's say, logistic regression or these kind of things. And their output has to be 1 or 0 only. It cannot be.
No. When you take logistic regression algorithm, the sigmoid function actually gives you a number between 0 and 1, and there will be a threshold. A default threshold is 0.5. At 0.5, the prediction is made.
Agree, sir. The outcome of that, based on the threshold, outcome of that has to be either 1 or 0. For example, if I
here in neural network, you will not use threshold inside the hidden layer. You will not use threshold.
Okay.
So that's the point I made. Any algorithm, threshold is not built into the algorithm. But the code who wrote it, like scikit-learn guy, he actually wrote the code in such a way that ultimately it takes the 0.5 threshold and makes the prediction. Got it?
Yeah, I understand that, sir. Ultimately, for example, in the hidden layer, let's take the top node, not x1 and not x2.
Okay.
There we will definitely fix some model, maybe internally or whatever it is. So its output maybe after the cost function calculation and then threshold, whether we define threshold or not define threshold, ultimately based on that model what we selected for that node, if it is, let's say, logistic regression, output has to be either 1 or 0. Is it not the case?
No, sir. No, that's what I am trying to explain.
Okay.
In the hidden layers, you will use sigmoid function only, not the logistic regression algorithm.
Okay, okay, sir. Okay.
I may have spelled it wrong. No, I am actually using logistic regression and sigmoid function as synonyms because we still not understood activation functions. Those are called as activation functions.
Sure.
Right? This is sigmoid function here, not the logistic regression algorithm. We know logistic regression, so I am actually talking. Yeah, your statement is wrong. If I spoke it as logistic regression, your statement is right. Sorry.
Maybe it's my misunderstanding, sir. Probably.
Yeah, no, not your misunderstanding. I am actually trying to, bridge the gap, but the terminology should be used exactly like sigmoid function. But if I say sigmoid function, you will get confused. But whatever your understanding is right, sir. The statements I made and your understanding are right. If I say logistic regression, the outcome should be 0 or 1. If I say sigmoid function, a number between 0 and 1.
Sure, sir.
Right? Now it is settled, right? So.
Yes, sir. It's clear, sir.
Yeah, it's clear. So, I actually took logistic regressions outcomes so that I can, demonstrate that we can build a simple neural network that can produce these values. And if I take a number between 0 and 1, right, then also I can take different weights here. Or the neural network will take different weights here in such a way that it will produce the y value. Right? For the neural network, what is the basis? The cost function. Cost function's basis is y value. It is always looking at y value and whether the algorithm is producing y value correctly or not, right? So, as Narayana asked, if I had taken the sigmoid function's outcome, these weights would have changed. That's the key, right? Deep learning algorithm tries to adjust these weights in such a way that the outcome, the y cap meets y. So even in machine learning, the linear regression, logistic regression, same thing is happening. In gradient descent, it is choosing some random numbers and adjusting them. I showed you already adjusted network. Okay, with a simple example. So here I wrote not x1, not x2 because it's a NOR gate, XNOR gate. Right? It's an XNOR gate. The XNOR gate can be represented as x1 and x2 and not x1 and or not x1 and not x2. So x1 and x2 is a this network. Here also, if you change these weights, right, it will not come. The y value will not come. So algorithm understood it in such a way that the outcomes are coming. Here it is not x1 and not x2. We combined both with OR gate, right? OR network. This is so you can actually create neural networks that actually represent these kinds of gates. Okay, and then we combined them, right? This is this is one network. This is another network, and we combined with an OR network. It's a simple example, and we kind of did that. But don't be worried about XNOR, all that. We have to be worried about these weights, these weights, these weights. Those weights are the goal of the deep learning algorithm. It will choose random weights, do multiple iterations, so that it can adjust these weights. How will it adjust? Back propagation. I'll show you what is back propagation in a moment. We actually see that. So is that clear? Good. Can I move on?
Yes, sir.
Okay, give me 1 second. So there is a terminology in neural networks that they talk about perceptron. Okay. Before the sigmoid functions, whatever thing came, people used to use the linear regressions outcome to make predictions on the logistic regression or the classification. So we have seen this, right? If the linear combination is less than 0, we say the record belongs to 0. If the linear combination is greater than or equal to 0, the record belongs to 1. Do you remember in logistic regression classes I have explained that? Let me open that slide also. Actually, we should jump into deep learning right after this. But there is some mathematical concepts like kernel trick and all that, right? PCA, SVD, those are all used in other areas. So if you don't have that understanding, using other algorithms is going to become difficult. That's where I kind of took that whole time and tried to explain. So if you look at this, I try to explain that if the linear combination, the z value is less than 0, the record belongs to 0. Right? The record belongs to 0. All the records falling in this side belongs to 0. All the records falling on that side belongs to 1. If z value is greater than 0, greater than or equal to 0, then record belongs to 1. That is perceptron. That idea is called as perceptron. Okay. So if you look at this here, if you look at this here, right, a perceptron takes several binary inputs, x1, x2, and so on, and produces a single binary output. Binary input 0 or 1 it takes, and produces a 0 or 1. Okay, we introduced weights right here, W1, W2. Those are the weights based on which it will try to, or it will learn these weights in such a way that the binary output comes appropriately. The neuron's output 0 or 1 is determined by whether the weights sum is larger or greater than 0 or less than 0, whatever. Greater than or equal to 0, less than or equal to 0 or greater than 0, whatever. It doesn't matter. Okay. So if you look at this, I have taken a scenario, right? There is a good weather, friend accompanying, is festival near to transportation, public transportation, then the person will go, right? Weather is good, friend is accompanying, and festival near to transportation. In America, I don't know, maybe you would have traveled, right? There is no public transportation available to every place, right? You have to have a car, right? That's a, I don't want to talk. So, you have to have a car, right? If you don't have a car, public transportation, nearby public transportation to any place you are going is must. So if all three are there, right? Friend is there, weather is good, weather is harsh there, and then public transportation there is there, the person is going. The friend is there, no, weather is good, friend is there, even though public transportation is not there, the person is going. If weather is good, friend is not there, public transportation not there, person is not going. So all three are not there, anyway will not go, right? So this is the training data set. Based on this, we want to understand, or we want to build a model. We want to build a perceptron model. Perceptron model takes binary input, produces binary output, right? So the perceptron model is what? A linear combination of the inputs that actually satisfies a threshold. So here I can say threshold is equal to 6. Let me try to draw this and explain. I am trying to explain what is perceptron. This is not needed, but interviews they'll ask. Some people who don't know deep learning, right? They'll get stuck to these theoretical concepts and they'll ask. So, so here, right, you can say that W1 is equal to 2, W1 2 is equal to 4, and W3 is equal to 6. So I can say this one as X1, X2, X3, and Y. Okay. Now the first equation is going to be the hypothesis function is going to be 2x1 plus 4x2 plus 6x3 greater than or equal to 6. That is the hypothesis function for the perceptron. Now if you put x1, x2, x3 into this, right, it is going to be 2 plus 4 plus 6, 12, greater than or equal to 6. That is true, right? This is 1. The record belongs to 1. Okay. Okay. Got it? Any questions there? Got it? Can I move on? If I put second record, right, it's going to be 2 plus 4 plus 0, right? That is also greater than or equal to 6. So this is also record belongs to 1, right? If you put this right, it's going to be 2 only. If you put this is going to 0. So they are less than 6. So we are saying the record belongs to 0. Now, right, I have got a new record, right? This is 0, this is 1, and this is 0. I need to predict, right? If I substitute that value into this, right, 0 plus 4 plus 0. No, it is not, right? So person is got, friend is accompanying, weather is not good, public transportation not there, person is not going, right? If friend is also not there, public transportation is there, right? This equation will give you 6. That means the person will go, right? So like that. So perceptron is going to take binary input and produce binary output, and it uses the linear equation and the threshold to make a classification, classification decisions. That is perceptron. Okay. Any questions?
So the output also always has only 2 classes. It's only
Yeah,
0
binary.
and 1.
Binary. If
Binary.
you look at the definition here, that a perceptron takes several binary inputs and produces a single binary output. Okay.
Yes.
Good. So let us move on to the next topic. Sigmoid neuron. We already know this, but I am actually trying to reiterate because you would have forgotten a little bit. Right? It's been a long time, and we have introduced lots of stuff in between, right? So artificial sigmoid or logistic neuron, we call it as logistic, not logistic regression. It is logistic neuron. Okay, artificial sigmoid or logistic, artificial sigmoid neuron or artificial logistic neuron. Simply we call it as logistic neuron or sigmoid neuron. So we need to, I actually already showed you this, right? When this is called as computational graph, right? When you have two variables a and b, and there is a function b that actually does some operation on this a and b, and there is a function j that does an operation on b. If you change one unit in a, you want to find how many units it affects in j. That's the key here in a deep learning, because on a deep neural network, what are you doing? You took all the weights, random weights, right, and tried to produce something. And in the next iteration, you are trying to tweak these weights, and these weights. When you tweak this weight, right, you wanted to see how much effect is happening on the y value or the error, right? So that same thing will have, I am trying to show in a simplified, function. Got it? Got it? So here, right, if you change a little bit, 1 unit, how many units j is changing? If you can find that out in a neural network also, you will be able to find that out. Or you can change the values in such a way that it is moving in right direction. If you know how many units it is changing, you can make it move in the direction you want it to, in the direction of error reduction, right? So here you can actually use derivative, right? What is derivative? Rate of change, right? dj by dA is when you change 1 unit in A, how many units in J is changing? That is what the derivative is, or the slope we call it as. If you look at this diagram, I changed 1 unit in A, 2 units changed in J, right? So I have taken A and J, right, on a graph to see the slope. The slope is actually going to let you know the rate of change when you change A. Okay, how many units you are changing, how many units it is changing can be known by slope. That slope can be calculated by derivative. That's how we came to derivative. I think we already know this, and I already explained it, right? So dj by dA can be calculated using a chain rule called as dj by dV and dV by dA, because when you change 1 unit in A, it will directly affect V. The V's effect will affect J. So when you change A, how much effect is, how many units in 1 unit in A, how many units V is changing, into in how 1 unit in V change, how many units in J changing, right? That you need to find out. So that is the chain rule. Okay. So here dJ by dV you can calculate. There are other sophistication is that when you are doing a derivative, if the function is if the function is in terms of the variable we are using, then you can calculate derivative easily. Rather, right, if you are trying to dj by dv, sorry, dj by dA, it's going to be 2v, right? There is no a term. It may sound like a constant, and constant derivative is going to become zero, right? It's not the theory, but it looks like that. So when you actually use chain rule, it gives you the flexibility to do the derivative very easily. Got it? dj by dv is equal to 2 because dv by dv is going to be 1, and dv by dA is equal to 1, right? dv by dA is 1 because dA by dA plus dv by dA, b is a constant when you are taking a derivative with respect to a. So this is 1, this is 2. We multiplied, we got 2. The same thing is evident here. When I took the data and tried to plot it and found out the slope also. Right? Got it? We covered this, right, before? Did we? Did we cover this before, or this is the first time you are looking at it?
We covered it, but
okay.
It's little bit complex.
So now also it's complex, or should I explain again?
I think now it is okay.
Okay, right. Let us see. Let us look at the total thing, and still we are not understanding, right? I'll come back and explain, right? So
but
why
I have a small doubt on the terminology, sir, here. So we said neuron is a single value, right? So what is this sigmoid neuron?
Neuron is a single value and it is outputting something. But inside neuron you have a function, right? Like this.
So can you please go to the initial diagram and yeah. Here, what is actually the neuron over here?
Sigmoid neuron, 1 by 1 plus e power minus z.
Okay. So that we say as a node, right?
Yeah.
Node in a layer.
Yeah.
So node and neuron both are same?
Yeah. Node and neuron are same.
Okay. Okay, sir, go ahead.
Okay. So there the function is complex. Here the function is simple. I took a simple function to explain the derivative will give you the slope. Okay. That's the thing here. Okay. Now this is the actual whatever you are asking, right? So if you pass x1 and x0 is 1. If you have only one input variable, right, then there will be a bias term. There will be a theta 0, I denoted as b, and there is a theta 1, I denoted with w1, and there will be a linear combination calculated, and then this linear combination is substituted into sigmoid function. This is the sigmoid function, right? 1 by 1 plus e power minus z, whatever z value you substitute it into that one, and the outcome is going to be between 0 and 1. This is the artificial sigmoid neuron or artificial logistic neuron. Is this what you are asking? Sesiram?
No, sir. My understanding of the neuron was different yesterday. Now it is Like the node and the neuron both are the same.
Okay.
My understanding yesterday was neuron was a single input value. So something like the x1, x0, sorry, not x0, x1, x2, x3, all individual input values are neurons.
No. They are input nodes. They call it as input nodes. And hidden nodes, we call them as. No, these neurons are hidden nodes. These are input nodes. They are individual values. In the hidden nodes are the sigmoid neurons or ReLU neurons. Right? There are different activation functions.
So the x1 is also a neuron here?
No, these are input nodes.
Okay.
These are input nodes. They are just values from your data set.
Yes.
Okay, here the calculation happens. Here the calculation. These functions, this function I am trying to dissect and show now. This function, if you have only one x and one x0, right, that's going to be like this.
Yeah.
The outcome is going to be between 0 and 1. That statement is same, but in the example that XNOR example, I took 0 and 1 to show it easily understandable thing there. Okay, so this is between 0 and 1, and the cast function is going to be again same thing. If it is a binary class classification, the cast function is going to be minus y log h of x minus 1 minus y log 1 minus h of x. H of x I denoted with a, that's it. H of x is I denoted with a. Okay. This is the cost function for logistic regression, right?
Yes, sir. Logistic
in neural
regression
network
binary
also.
classification.
Yeah, in neural network also, if the last node is if the output node is a logistic regression node, then the cost function is going to be same. If the output node is a the softmax regression classifier, then the node is going to the cost function is going to be cross entropy. This is cross entropy with two classes, right? Cross entropy is the cost function. If the output node is linear regression, then that you can take RMSE or MSE or whatever. You can choose the cost function there. Okay. So one simple sigmoid neuron I am actually showing, and let me go through the whole thing and then I'll stop for questions. Okay. So this is this is how it actually looks. And now forward propagation. What is forward propagation? Right? Think that it is a neural network. Right? It is not a neural network. I'll show you neural network, but think that it is a neural network. In forward propagation, what happens is it calculates linear combination and then substitutes into the whatever activation function, and then substitutes into cost function and calculates the cost. That is the forward propagation. Simple, right? Multiplies, sums, then substitutes into logistic regression, and then calculates the cost by substituting into this equation. Okay, that is forward. Back propagation. Gradient descent is the algorithm it is using, right? So what is back propagation? In the first iteration, it chose W1 randomly, B randomly, calculated, substituted, calculated, and stayed there. Now it need to adjust W. When it is adjusting W, right, it should adjust W in such a way that the J will reduce. The goal, optimization objective, we call it as. The goal of the algorithm or the optimization objective is to reduce the cost. So if you know how many units, when W is changed, the J is changing, you can actually control that by using alpha. That same gradient descent algorithm. So if you change W, right, W we are changing in such a way that in the direction in which the the 1 unit change is affecting J. W1 minus alpha into dJ by dW1. So W1 minus alpha into dJ by dW1 can be calculated using dZ by dW1 into dA by dZ, right? dG by dW1, because when you change W1, G is changing, Z is changing, or you can directly calculate derivative of the Z because it is in terms of W1. Okay, and then you can calculate the derivative of j with respect to z, because you know the z function, j function is in terms of sorry, you need to take this also, sorry, dj by dz is equal to dj by da into da by dz. So let me try to write it in a simple way. Give me 1 second. If you look at that, right, it may be confusing. So this is like, this is how it is. W1 is equal to W1 minus alpha into, you can directly calculate this function derivative using W1 because it is in terms of W1, right? dz by dW1. Dou I am putting there. Okay. And then you can calculate A's derivative using z, because the function is going to be 1 by 1 plus e power minus z, right? So you can, I think I should have 1 by 1 plus e power minus z, right? So you can calculate the derivative of a with respect to z because it is in terms of z, right? It is dA by dz. Okay. Now the cost function is in terms of see that cost function is in terms of a, right? The cost function is in terms of a. So you can calculate derivative of the cost function with respect to a, dj by dA. So this is the slope. This is the slope of the tangent at W1. Cost function is convex, right? We chose some W1 and then we are calculating that slope. This is the slope, right? And then we are subtracting that from W in such a way that it actually moves a little, you know, forward. Our goal is to reach to this place, right? When you calculate this derivative will become 0 here. And then W will stay there only. How many iterations you move, W will stay there only. These random W's will be adjusted. Now, forward propagation will actually calculate the cost, and backward propagation is going to calculate this equation. There is nothing moving backward, but it is calculating this value and then subtracting it from W1. Right? For B also the same thing, right? B is equal to B minus alpha into derivative of z with respect to B, because it is in terms of B, right, into dA by dz, right, because A is in terms of z, right, this equation, and this equation is in terms of A, so it's going to be dj by dA, right? So that is the B calculation. Next iteration, B calculation. Right, like that it will actually do forward, backward, forward, backward, forward, backward. Forward it will calculate the cost, backward it will adjust the weight. Forward calculate cost, backward adjust the weight. Forward calculate. So our goal is to reach to a place where the cost is low, but the cost is low will happen when the slope becomes 0. The slope becomes 0. When the algorithm is moving, the slope becomes 0. Got it? Got it?
Yes, sir, but the forward propagation and backward propagation happens the same number of times. Like the forward propagation is calculating the cost.
Same number of times only, right? If you say 10 iterations, right? First iteration it will go forward, right? Again back propagation, forward, back propagation, forward, back propagation, like that. 10 iterations.
So, yeah, forward propagation is calculating the cost. And backward propagation is just adjusting the weights.
That's it. Okay. So it is actually looking into cost, you know, here it is looking into cost.
It looks into the cost and adjusts the weights.
This is simple, whatever we learned, that logistic regression. Right?
Yeah, there also I had the same kind of confusion. So
that's okay. You know, even if we need it, right, we'll cover this tomorrow also. You have a look at it. come back with questions, we'll cover, right? We'll go back to that gradient descent and cover it also, because if you understand this concept and the other concept I explained today, right? This, not this one. These weights thing, right? That's it. Deep learning is done. Deep learning is not, there is nothing in deep learning. Very simple it is. Adjusting weights is the deep learning. That's it. You take more algorithms and try to combine them as a network, and it is adjusting weights. How is it adjusting? That's what I am trying to show now. Right? If you understand first 4 classes well, in deep learning, rest is all easy. Okay. So we'll take time if needed, right? 1 week we'll take, but we'll not leave until we understand. So here, right, I wanted to highlight one point. If you look at this term, that blue term here and here, is that same? The blue term is same, right?
Yes.
Right. So if you are implementing, right, no need to implement, because the TensorFlow, PyTorch, these modules already implemented it. Right? If you are trying to implement manually, if you calculate these two terms at once, right, in a neural network, that can be used in all the nodes. Only this term will change. Okay. Why am I explaining this is Andrew NGA has got a course in Coursera, artificial intelligence. In that course, right, he'll ask us to implement it. They'll actually implement most of it. They'll give blocks here and there. We need to implement it. This is one of the exercises. That this part is once implemented is enough. These we need to calculate there. Right? So just for I recommend you to do that certification, because that is more famous than all these InsoFA and all that stuff. Okay, local whatever. So let me move on and explain a little more, and then I'll stop for questions. So that is the neural network. That is how a sigmoid neuron is actually calculating. Okay, the next weights, right? Gradient descent, back propagation, right? This is, I try to actually do it more elaborate way. So this is how it is actually happening. Right? This is sigmoid neuron. Let us look at a simple neural network. What I'm trying to show here is how sigmoid neuron is calculating the next weights is same as in the neural network also. Whether you have one function between, whether you have two functions between the cost function and W, or n number of functions in between cost function and W, it doesn't matter. The same formula applies and same approach applies. Back propagation and forward propagation will not change. So let us look at that. So I have taken a simple neural network where I have one input layer, one hidden layer, and one output layer. Okay. So here I have two inputs, x1 and x2, and x0 is bias term. So I for simplicity I actually denoted the weights going into this node as W0, W1, and W2. The weights going into this node, I said this neuron, I said W0, theta 0, theta 1, theta 2. If you can see that carefully, see that the Z1 calculated using W0 x0, W1 x1, W2 x2. Z2 calculated theta 0 x0, theta 1 x1, theta 2 x2. Okay, just for notational purposes. Even in real time, these values are going to be different. W's are going to be different, thetas are going to be different. Randomly chosen W's are different, thetas are different. Okay, and then we calculate Z1 and substitute that into logistic function. We get A2, A1. Okay, I took A0. In every layer, we'll have bias term. That bias term is this one. That actually adds the intercept U0, right? So U0, U1, U2 are again constants. Right? They are weights, right? Random weights chosen. And then you calculate Z. Substitute that, you get B, and now you calculate cost. Okay. So this is a neural network, simple neural network with one hidden layer. So that is first iteration. Random weights, first iteration. Second iteration. Second iteration is going to be like this. W0 is equal to W0 minus alpha into dj by dW0. W1 is equal to W1 minus alpha into dj by dW1. Right? U0 is equal to U0 minus alpha into dj by du0. U1 is equal to U1 minus alpha by dj by du1. I did not take W2 also here because it is becoming complex. No, the diagram is becoming complex. So here I took W2 also, X2 also, but in this diagram I did not take W2. Okay. So this is back propagation. Right. So to calculate the dj by dW0, what we need to do? So here, right, I need to calculate next W0, next W1. Suppose that I am calculating next W1. So to do that, I need to do W1 is equal to W1 minus alpha into dj by dW1, right? So this dj by dW1 can be calculated alpha into dj by dW1 calculated as dz1 by dW1 into, right, when I change one unit in here, how many units is changing here? So in a neural network, more functions are included, chain rule becomes big, right? The chain rule becomes big. On a simple example here, the chain rule is small, right? On a sigmoid neuron, chain rule is a little big, right? On a neural network, the chain rule becomes even bigger. Okay. When I change one unit in W1, Z1 will change. Right? When you change Z1, A1 will change. A1 by dZ1 into, when you change A1, right, the Z will change here, right? dZ by dA1. When you change Z, right, B will change. So dB by dZ. When you change B, J will change. So dJ by dB. Right? Chain rule became big or not? In the sigmoid neuron, we have three terms to calculate dj by dW1 because the number of functions between W1 and J are less. On a neural network with one layer, we have got five, right? Five terms. 1, 2, 3, 4, 5 terms because there is one more function added here, right? If you have 100 layers, right, this calculation becomes big. That's it. Got it? For W0 also same thing. For U also same thing. For U0, U1 also same thing. Got it? Back propagation. Got it? Any questions? Everybody is silent. I am scared. Any questions?
Can you please repeat it, sir?
Okay.
So the propagation.
Sorry.
The chain rule. Okay.
I'll repeat it. I'll just take the new slide and try. Don't look at all these calculations. Okay. Once you understand the concept, right, you look at the calculations, you will understand. See, it took around, I think, 1 month or 2 months for me to understand and engulf everything. I am trying to explain in 1 hour. It is difficult. It is a simple trick. It is not difficult. So you need to get that trick. So it will take time. Don't be disappointed. I am here to help you, right? Our goal is to learn deep learning and NLP. Those all, whatever we are learning is all for fundamentals. Okay. So here, let us look at one path. We take another color. I will say that is one forward path. Right? That is one forward path. Okay. So I have to calculate, forward propagation, right? The W, W0, W1, U0 values are there. You are going to substitute that into linear combination, calculate the sigmoid, and then calculate cost, right? That part is clear, right? Forward propagation is clear, right?
Yes, sir. So W and W0 are weights in the first step, and U1 and U0 are the weights in the second step.
Second layer.
Second layer. Okay.
This is first layer, this is second layer.
Yeah, this U1 will also come
layer.
into.
This is output layer, this is hidden layer.
Okay.
Okay. So now back propagation, right? What is back propagation? Need to adjust this W, right? So to adjust this W, we need to calculate next W. Next W is equal to W minus alpha into dj by dw1, because that is the slope. Right? dj by dw1 is the slope, and we are reducing that by controlling with alpha. And that's gradient descent algorithm. How to calculate this dj by dw1? That's the question I am trying to answer. Right? To calculate dj by dw, what is the dj by dw1? When you change 1 unit in w1, how many units in j is changing? Right? So if you want to look at the j's function, it is going to be very complex. Or if you want to write j function in terms of w1, it is going to become very complex function. Do you agree with my statement?
Yes, sir, that's right.
Right? Mathematics, you think about mathematics, right? Right? If you want to write a j function in terms of w1, it's going to become very complex. A big equation will come. We don't want that. We don't want to create a big equation. How to simply do it? Right? When you change w, z will change. If you find out the units change or the slope, right, of z1 with respect to w1 and a1 with respect to z1, right, because the equation here is in terms of w1, the equation here is in terms of z1, the equation here is in terms of a1, right, the equation here is in terms of z, the equation here is in terms of b. So doing derivative of the next function is very easy. So that's what we are taking the path. W1 is equal to W1 minus alpha into dz1 by dw1 into, right? I took derivative of this one with respect to this one into chain rule I am using, okay, into dA1 by dz1, right? When I change z1, how many units in A1 is changing, right? When I change A1, Z is changing because A1 is a term in that equation, right? So how many units in Z is changing? dz by dA1. When I change Z here, B is changing. How many units in B is changing? dB by dz1, Z. And when I change B, J is changing. So dJ by dB. So this whole equation will calculate this value. Is that clear? Is that clear?
Yes, sir. But we are actually representing the Z in the second step, that is the output layer also, right?
Yes and yes.
So in the hidden layer, we are representing Z in terms of W, and in the output layer we are representing Z in terms of
hidden layers output. Hidden layer output A.
Yes. Okay.
Hidden layers output A. So this is A1, this is A0. A0 is the bias term, A1 is the first hidden layers output. If you have many nodes, right, A2, A3, A4 all will come here.
So can we represent this the second Z in terms of something else? It's just the mathematical representation.
Something else. How can you represent it? It is a linear combination of the inputs, right?
No. Sorry. Instead of Z, can we represent with something else? The equation should be same. We cannot change the equation, but the representation of Z.
You can take any letter there.
Any letter.
I have
Yeah,
taken my own letters here.
Okay. So
There is no hard and fast rule. This is all mathematics, sir. So you can take any variable name. I took these variable names because I thought it is easy. 1 minute, sir. 1 minute. Hello. Sir, good morning. నేను ఒక్క 2 నిమిషాలు చేస్తాను, క్లాస్లో ఉన్నాను. 2 minutes. Yeah. A terminology, right? That terms you can take anything, Z or A or whatever. But now when I looked at Andrew Ng's notes, right, it looked very confusing because he took the same variable names and he created a multi-dimensional arrays and all that. It's a very clumsy thing. So I tried to demystify it and try to show. If you get time, right, try to look at Andrew Ng's notes on YouTube. You will find, I don't look at it because it's a very confusing. If you want to understand it in a different way, you can look at it. So Narayan garu, did you get it?
Yes, sir. I got it.
Okay. You are worried about mathematics, right? That's what I'm actually trying to make sure you got it. There is now you just need to understand that we are calculating each step the value, and then multiplying them. That's it. Each step the change in value and multiplying them. That's it.
Yes, sir. Yeah.
So here, right, I took this much time and tried to explain because if you look at this particular term, let me take another color here. Right? If you look at this particular term, what is that dA1 by dG1, right? It's a derivative of an activation function. This is an sigmoid activation function. This is right. In neural network, in the hidden layers activation functions, we take derivative. That point you need to remember. In a logistic regression node, you never take derivative of activation function. Let me show you that. That's the difference between simple logistic regression and neural network. If you look at this, right, in this sequence, I have written notes, right? So in this, right, yeah, in this also we are taking, sorry, dA by dJ we are taking, right? So in linear regression, you yeah, when you do the cost function, when you multiply the cost function and take the whole thing, there is no activation function comes when you are taking derivative. But in logistic regression and deep learning, you have to calculate derivative of the activation function also. In this whole term, one of the multiplier is going to be derivative of the activation function. This point is important. We'll see that tomorrow. Okay. Are we good?
yes, sir.
I'll start with the same thing tomorrow and go a little forward. And I think there is another function. Yeah, this is the function. I'll explain the activation functions now tomorrow. And tomorrow's class is going to be till 8:30 only. Try to join on time. I have another seminar, and we'll stop